Today we will discuss about the ammeter, and ammeter is actually the modified form of galvanometer. As we unboxed the galvanometer in the previous lecture, and we saw that inside that galvanometer we have a coil. So here this red like shape is a coil, and inside the coil we have the iron core, which is used to provide the permeability for the magnetic field produced by this coil. And we have this external magnet, and this is the north side pole of the magnet, and this is the south pole of the magnet, and this magnet make a concave like shape in order to provide the 90 angle at each and every position of this moving coil. Okay, so here this was the construction, and we discussed this in the previous lecture. And these are that spring. This is that spring which provide the restoring torque. Okay, so in this lecture we will convert this galvanometer into ammeter, and ammeter is actually the modified form of the galvanometer. Okay, above this position, above this we have the galvanometer. Okay, and here we attach the resistance. Okay, this is actually a resistance, and we attach this resistance in parallel with this galvanometer. Then we call this as ammeter. So here is the circuit diagram. So in this case we have this galvanometer which is above from this position. This is the galvanometer. Okay, and we attach the resistance in parallel with this galvanometer, which is shown here. So this is, we have the galvanometer and we attach the resistance parallel with this galvanometer. Now if we attach the source of EMF as a battery, okay, so here the one side of the battery is attached to here, and the other side of the battery, the other terminal of the battery is attached to here, due to which the current will start flowing in this. Okay, and that current direction is from here, and it will pass through the galvanometer. It will show the reflection, and after that it will again come to the other terminal of the battery, and similarly this current at this position will be divided. So when the current is come from here, so here it will be divided, and some of the current will pass through this resistance. Okay, and some of the current will go into the ammeter, the galvanometer. Okay, so here is the same circuit. We have this external battery. Let's say this is attached to positive terminal of the battery, and this is attached to negative terminal of the battery, and we have this is the direction of electronic current, and we call that current as I. Okay, we have that current as I, and here at this junction this current will be divided, and some of the current will pass through this resistance, and some of the current will pass through the galvanometer, as I have discussed here. So at this position some of the current will pass through this galvanometer, and some of the current will pass through this resistance. So we have that same case. Okay, so the current pass through the galvanometer, here the current is passed through galvanometer, we call that as Ig, the current from the galvanometer. Okay, and this and here some of the current will pass through this resistance. Okay, so we call that current as I, and this this resistance we call a shunt resistance. Shunt resistance is actually the resistance which is attached in parallel with this galvanometer, and we call this as a shunt resistance. Okay, so here this is Is, the current passing through shunt resistance, and here Ig, the current passing through the galvanometer. Okay, so this galvanometer will have some internal resistance, and which is given by R. Okay, G. Rg is the internal resistance of this galvanometer, and the internal resistance of this shunt resistor is Rs. the resistance of this shunt resistor. Okay, so we call this resistance as Rs, and the resistance of this galvanometer is Rg, and the current passing through that galvanometer is Ig, and the current passed through this shunt resistance is Is. This is Is. Okay, so here at this point so this is the current I. At this point the Kirchhoff current law is applied, and let's say that the current entered to the junction is equal to the current leaving the junction. So here, according to the Kirchhoff's current law, the current entered to this junction, which is I, is equal to the current leaving this junction, which is Is plus Ig. Okay, so from here we can find the current through shunt resistance is 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 equal to I minus Ig. Okay, so in this case, if we provide the external current, okay, the current which is show full deflection on the galvanometer will pass through this, and the remaining current will pass through this shunt resistance. Okay, so this resistor and this galvanometer is present is attached parallel to each other. Therefore, when the components are attached parallel to each other, their current will be different and the voltage will be same. So the voltage from this the voltage of this galvanometer is given by Vg. Okay, and this the voltage of this resistance is this shunt resistor is given by Vs. Okay, so these are connected parallel to each other. Therefore, the current will be different in parallel case and the voltage will be same. So here the voltage is the same. Now, according to the Ohm law, V is equal to IR. So here I can write that I and R. Okay, so this is Vg, so Ig R of galvanometer is equal to V is equal to I and R. So from this equation, the shunt resistance can be determined as Rs is equal to, so if we divide Is on both sides, this Is will be cancelled. So here this become Ig R of G divided by current of the shunt resistor. Okay, so as we know that the shunt resistance is equal to I minus Ig, so put that value. So this become R is equal to Ig, okay, and Rg divided by that current Is. So instead of this current through shunt resistance, we will put this value, which is I minus Ig. So this is the equation for the shunt resistance, and that equation is R of shunt resistance is equal to current through galvanometer and the resistance of the galvanometer divided by the total current minus the current through galvanometer, which give us the shunt resistance. The resistance of this resistor, okay, which is connected in parallel with the galvanometer. So here, for example, if we provide the current from the external battery as 10 ampere, okay, this is the total current from the battery, which is called the I in this case. So if this current is 10 ampere, so at this position that current will be divided. So let's say 2 ampere current will go through this galvanometer. Okay, so this is actually a sensitive device which required very less current. So for that, let's say that Ig is 2 ampere. Now the remaining current will pass through this shunt resistance. So the remaining current Is is given by this formula, which is equal to I, and I is given by 10 ampere, and this is minus an Ig. Ig is given by 2 ampere, and this is equal to 7 ampere. Now the question is arise that in 10 ampere current, only 2 ampere current is passed through this galvanometer, and due to which this galvanometer show deflection. Then what about that 7 ampere current which is passed through this shunt resistance, and how to trace that 7 ampere current? So for that, the engineers determine the ratio for the Rg by Rs. So this is the fixed the resistance of the galvanometer, internal resistance of the galvanometer, and here we have the resistance of the shunt resistor. So it will have some value. Let's say this value is 10. Okay, so if we have this value, so the deflection present here on this screen, let's say that deflection is 5 ampere, and due to the current passing through this galvanometer, it showed us this deflection. Okay, so in order to include this current as well with this, then we will multiply this 5 current with this ratio, okay, with this 10, and it will give us the 5 multiplied 10 is 50 milliampere. In some ammeters, they label that if you have the current shown by this galvanometer, you will have to multiply some factor with that current. So here in the ammeter we have that same galvanometer, but only the extra shunt resistor is attached in parallel with that galvanometer, and if we provide the current through this okay, some current will pass through this shunt resistors, and some current will pass through this galvanometer, and due to that current passing through this galvanometer, it will show some deflection. Okay, and as the large current will pass through this shunt resistor. Okay, in order to include the effect of this shunt resistor, we will find here the ratio of the let's say we will find here the ratio of Rg, which is given. So the internal resistance of the galvanometer we know. Okay, and it is also known the resistance of the shunt. So if we find the ratio, it will give us some value. Let's say this is 10. Okay, and here in this situation, when the current is passing through this galvanometer, it will show some deflection. Let's say 4.7 milliampere. Then we will multiply that 4.7 with this factor, and that will become 47 milliampere. So here the last point is to be remembered that this Rs is always less than this Rg, because here the more current is passing through this resistor. Okay, so if the resistance of the resistor is less, then more current will pass through this, and here the less current is passing through this galvanometer, therefore its resistance is less. The resistance is more as compared to the resistance of the shunt resistor. Okay, so that's it guys, thanks for watching.